Okay, so that's the connection. By the way, we still have boundary conditions, right? This is a boundary value problem. So we've got that set up. What are the boundary conditions? Well, let's come back over here. My boundary conditions were that at x equals plus or minus 1, this thing is 0. But what is psi? Psi, we said, was y1. So y1 at 1 or at minus 1 is 0. So that's our translation of the boundary conditions. So here are our equations with the boundary conditions. I'm going to put a box around that just to know how important it is. There it is. That's our whole problem now. System of first order equations. Okay. So now what we're going to do is we're going to develop a shooting algorithm. It's going to take off. So let's try to draw a picture first. Remember, never do this blindly. We're going to have to play around a little bit so that we kind of know what we're supposed to be looking at. Right now, we don't even know what beta is. We don't know what this is. We don't know if there's any constraints on it. So let's take a look at this thing and say the following. What we have here, then. I know the solution has to be here, and has to do something in between. Okay? Now let's look really quickly for a moment at this equation. And let me look at it from this perspective here. Let me take this to the other side. So here is our initial, this is our differential equation inside of here. Okay, just move to the other side. Now beta is constant. So let's just try to ask a few questions about this thing. So 100 and beta, so this is a sort of another constant. And suppose beta is bigger than 100. Okay? So if beta is bigger than 100, then beta minus 100 is a positive number. Okay? So if you have something that looks like this, where a is positive, the solutions to this, anybody know what they look like? They're exponentials. Okay. So they are solutions like this, e to the plus or minus square root a x. So let's ask the following question. Ready? I want a solution that starts here at 0 and ends at 0. Can you draw for me an exponential that leaves 0 and ends at 0? Try to do it on your paper. You could totally do it. Watch. I make this a little bit crooked, and then that totally works. So if you really are bad at drawing, you can make this happen. But if you actually try to be reasonable at drawing and mathematically correct, there's no way an exponential takes turns. Exponentials don't take turns. They just go to infinity, or they go to 0. Okay? There's no way these solutions could ever meet our boundary conditions. So what does that tell us? It tells us that beta better not be bigger than 100. Right? Okay, so beta could be less than 100. Does that make sense? Now, if it's less than 100, sorry, that's really bad handwriting. Sorry. Okay, we'll leave that there. Now, let's do the opposite. If beta is less than 100, then I have a negative number here. So this is going to be negative here. So what do solutions to that look like? Now, this here, hopefully you saw that, right, in typically you would have seen it either in differential equations course, or you would have seen it like in the third quarter of the physics sequence. Called it simple harmonic motion. Do you remember that? Two derivatives equals to of something equals a negative constant times itself. Cosines and sines are the solutions. Now we're in the game. Why? Because a cosine can take a turn. So can a sine. Right? So you can imagine a cosine could do this. A sine could do this. I don't know if those are solutions, but at least they have the potential to meeting the boundaries. Okay? That's it. So this is good to know. So ahead of time, what we know already is beta has to be less than 100 for this problem to even make sense. Okay, so let's put that little fact here. Beta less than 100. All right. Now, we don't know much else yet about the system. But before you start building a routine to solve it, you better kind of understand how does this thing behave a little bit. Okay, so we're going to program it up and start looking at that.